All right, week 101. What is up, everyone? Let me get the music going. Welcome to another week, another year of streaming myself. Yeah, okay. Coming a little bit off of a cold, so that's why my voice might sound a little bit stuffy, but we're out here, and I think the tweet went out. All right. See if the chat widget catches up, but yeah, welcome everyone. 2026, stream 101, and today, virtual memory is still the topic, but I've been doing a lot of thinking, and I'm wondering, I might change my approach a little bit. So far, I've been doing this very unit test heavy approach, and I might cool off with that. What's up, Caflare? Hello. Yeah, I think I might chill out with the unit tests, to be honest. I think the idea sort of works to have a unit testable kernel, but what I'm realizing and what I've been researching is that there are a lot of limitations to what I can even reasonably unit test in the kernel. And also just slows down progress quite a bit. And so I'm sort of checking in to see if it's still worth it to continue with this unit test heavy approach. I think it's a good idea to have the infrastructure for it, and I think that was a worthwhile investment, but I think, yeah, I might take a bit of a different approach kind of going forward. So working on WebSockets and search hat. Nice. That's cool. I guess, do you find that doing web development sort of, I don't know, makes you think differently than doing OS development? Or I guess, how does it feel? I feel like, I mean, those are super different things, and you've worked on both sides of them. I've never really done a lot of web development, so I'm not really sure. I mean, I can imagine it's easier maybe, but maybe it's more difficult in other ways. That's cool though. For anyone watching the stream, Catflare is working on a Discord clone, Discord killer. All right. Nice. What's up, Kamal Deep? What's up, Kedar Codes? Nice to see you. Immediate feedback on my website, and you just tell me what I can improve, how to fix. Nice. Yeah, that's cool. Yeah, it is nice to have feedback, user feedback. Okay. So yeah, I think I have a couple plans for today. Maybe quick recap on what we've been doing so far, but whatever. So yeah, plans for today. I want to actually test out the virtual memory implementation within QEMU. And for example, just do some basic mappings and test out that like still even works at all, basically. Because so far I only tested the virtual memory mapping code within the unit tests, and technically those are passing, but you never know how well they really represent reality until you've actually run it in production. So that's plan number one today. I want to try to just actually in the real kernel try out my virtual memory code and just map some memory and then just try to access it. Yeah. And then step 2 is probably continue working on the unmapping, the memory unmap, which might get interesting because we'll need to figure out how to ref count the physical frames. So that should be interesting. Kamaldeep, I'll hit you with my resources command. I haven't read any books other than following the MIT course, which doesn't count as a book, to be honest. I've read a little bit of the XV6 book, but I don't know. Yeah, I think there's some books on that resources page. Okay, let's just see how are we building? Our build is working. Let's just check in on the state of the code. Open recent JAWS. So last time we were kind of digging into the unmap function. And I was doing a little bit of slightly vibe coding it out. Just a super basic implementation that goes through the page tables and unsets the present bit. It sets the unpresent. It sets the page table entry to be unpresent and then walks up each layer of the page tables, possibly setting more of those bits to unpresent. And yeah, basically freeing page tables if there were no more present entries in a particular page table after freeing one, which I thought seemed like a reasonable idea. And we even got some basic unit tests working for that, if I recall correctly, where I'm able to instantiate the address space, map something, and then kind of save some pointers to page tables, do an unmap of a virtual address, and then verify that all of the corresponding entries are no longer present. So that was nominally successful, but it's still a super half-baked implementation, and frankly, I don't even know. Yeah, that was just kind of the first step. What's up, filthy potato? You're a smart man. Thank you very much. I don't know. I've just been doing this for 2 years, and I wouldn't even say I really know what I'm doing. Okay, so I think here's the part where I'm gonna do that gear switch that I said I was going to do. So let's go and let's just try to do this kernel thing. So okay, let's clear this out. K-main CVP. So yeah. I mean, really, here's where we left it off. Just for a check-in, what does the kernel look like these days? It doesn't do anything. It just like boots up, gets some info from the bootloader, and then crashes. And so, yeah, so here's what we're going to do. This is sort of getting us off to a start. What's up, Moose? Issue this week? Issue this week is testing out the ultra basics of whether mapping a page of virtual memory like works within the kernel. We've only ever tested it in the unit tests so far, and that sort of bothers me, and so gotta get you on NeoVim. Oh man, sell me on it, pitch me on NeoVim. I just sort of got used to VS Code, and I also sort of like this test extension where I can run my unit tests off to the side. I think NeoVim has that too, but it's just sort of nice. And also the debugger view on the left is kind of cool. Okay, so here's what we're going to do. We're sort of close. The idea, we're creating the virtual address space. We're passing it a PML4 table that we manually allocated here. Gotcha. Increased productivity. I do use the Vim extension for VS Code. I'm not necessarily the best at it. Okay, cool. So, right, so we set up the virtual address space. What's up with this? We're allocating a new frame of memory, right? And we're going to map it at some destination. And this or like hex 100,000 was the test destination. That we're going to use. Okay. So I'm just going to do a couple things. I'm going to take a look at the memory map. What I want to try doing is installing my own basic set of page tables. And the immediate first problem we're going to run into is that the kernel, as soon as we engage the new page tables, the kernel's code is not going to be mapped anymore. And so we are going to crash. And so at an absolute bare minimum, the kernel needs to still be mapped. Oh man, Filthy Potato fell in love with the debugger. Man. Nice. What's up? So Dave Sharma. I learned everything I know about this from this MIT course that I took in the first year of streaming. Gonna marry my debugger. Go for it. That sounds lovely. Yes, the course material is free. Yes. Digitalized. What is up? First stream of 2026. That's right. That's right. Starting the year off the right way by doing some computer programming. Okay. Right. So, yeah, my goal, install the page tables and have the kernel not immediately crash. Actually, yeah, this is all. So in order to do that, I need to set up some extremely basic mappings. Literally, the only thing that will be mapped is the kernel. And in order to do that, I need to answer some questions. I need to know, where does the kernel live in physical memory? So I can map it. Where is the kernel in physmem? Right, that's mandatory information in order for me to set up my basic mappings. What's up, Bazarazib? Happy New Year. Nice to see you. Okay, and that's a question I hope to answer by looking at the phys map, or the memory map. Okay, and then second question is, where is the kernel currently mapped in virtual memory, so I can recreate the mapping. Also, I probably need to make the map thing RWX for start. Right. So these are just some thoughts about how to actually do this. And yeah. So Filthy Potato, you don't really sign up for the course. You just sort of do. What I mean is that you just go and do the labs. And so here's the website, lab 1, or these other things, and you just do all the labs. That's pretty much it. You don't you can't sign up if you're not an MIT student. All I mean is that they publish all of the resources and stuff, and those were enough to help me learn a lot about this. All right, let's start answering some of these questions. Where is the kernel in physical memory? It is here, executable and modules. So here's what I'm thinking, and just curious, phys base, right? Phys base is the physical base of where the kernel is loaded, and it's consistent with what we see here, F0 B1000. And then we have this range with the E1000 length, and so that's kind of the answer to that first question. That's where the kernel lives in physical memory. Okay, so these questions are not too hard to answer, to be honest. Okay, second question. Where is the kernel currently mapped in virtual memory? Also not super hard to answer, at the vert base. And so this is the mapping that I'm trying to create right now. So let's give this a shot. You ever look things up to help out, or do you try max brain power? Oh, I look stuff up all the time. Let me take that back. I sort of avoid Googling things. I will sometimes ask AI for help on certain things, but my first step is to try to think about it and then look at the manual, like the CPU manual or whatever. And actually that has been going pretty well so far. But there have been times I've ran into things, but actually, yeah, no, I've been able to sort of avoid doing too much Googling. Okay, so to map. So we don't even have a convenience helper. The address. We have no we have like no convenience anything at all. All we have is kind of a stupid function that maps a single frame of memory. So yeah. And what might be nice would be to build, I don't know, some kind of additional abstraction layer that allows mapping ranges of memory. So I'm going to keep this on the left and I'm going to move over to the right. In typical kind of sketchy code, I'm just going to start out like this. And so map range, bool. And we're going to take a starting virtual address, physical address, and then int size. Yeah, what's the name of that? The size of how map p-adder at dest v-adder. We're going to need to take a v-adder space by reference, for example. And I'm super tempted to try to vibe code it, but I'm going to not do that so I can exercise my brain. So here's what we're doing. We're just we're just kind of iterating through page offsets all the way through. Maybe we can do some assertions. Is aligned. Okay, page size. Maybe that's useful to do. We're going to assert alignment on everything to make it simple. Set stan size, set plus equals k page size. Okay, we're just doing this loop. And it's going to be something along the lines of va.map. And it's going to be dest v-adder plus offset at maps to p-adder plus offset. And then what's the return value? What happens if the operation fails? That's a little bit of an awkward situation. Yeah, what if it fails halfway through or something? Then we can return early and just return I'm even sort of wondering what this implementation is doing. Right. Return whether the mapping succeeded or if it failed because something was already mapped there. We are currently not handling out of memory errors. I think we assert. Actually, no, we return a physnal pointer, which all these things are missing checks for. Yeah, with this to do. Okay, ignoring that for the moment. So I'm just going to do how to handle errors. I don't know. We can return false halfway, but it leaves the page tables in an inconsistent state. Truly, yeah. I don't know how to. We have some options there. We could do the simplest stupid thing of just kind of leaving it like that. Just to, as usual, the venerable JOS is the OS that I'll reference when I'm trying to answer questions like this. But actually, yeah, I'm trying to, where would that be? So this is kind of an example of a somewhat equivalent situation. And I think, yeah, this is also the case where we're mapping ranges, a range of virtual space to physical space. And I think JOS does not do error handling. It simply asserts everywhere. So, yeah. So maybe that's the answer for how JOS handles it. It just kind of doesn't. And yeah, that's probably not so acceptable, but whatever. Turn true. But I'll just do the same thing for now. It did succeed. I'll just add an assert. Good. All right, so here's my basic attempt at sketching out a function. What's the, right, it's in a header, so I'll just temporarily add inline to make that work. And then now I can ostensibly map a region of memory. As usual, there's always the question about overflow detection. Offset can overflow if size is too actually, wait a sec. Yeah, what about overflow is kind of interesting in this case because num bytes and offset are both integers. And we start from 0 and just sort of work our way up to the size. So in the worst case is the size is like int max or something like this. I wonder if that's actually an infinite loop. I think I would need to think a bit more about that. Because int max is not page aligned, I think. Let's just say, for the sake of example, right. That does not, okay. Yeah, right, obviously it's all ones. And so actually I don't, for looping all the way up there, then on the last frame, we're going to try to increment offset past int max. It's going to overflow to a negative number. And that is obviously going to be very bad when we try to add it like this. So for the moment, I think an assertion. But to be honest, yeah, this is not something I've thought about super in depth, and I'm not sure what the most professional or idiomatic approach to overflow detection is in a case like this. But I think it could happen actually, and maybe even infinite loop, because offset's going to be climbing all the way up to num bytes, right? And if num bytes is int max, then offset will get kind of close to that. It'll be at the lowest page aligned kind of offset. It'll work. Will bump it up one page size, which will go one past int max, which will overflow down to negative, and that will still meet this condition. So maybe another alternative is to include that in the condition, or include offset greater than or equal to 0 in condition. That'd be a question. We can look into that later. What's up, mode? No, unfortunately not. This project is not on GitHub for the moment. Just a little private coding project. Okay, so here's my bad map range. But even though it's kind of bad, maybe it's good enough to kind of keep going with what I want to do here. And so now the idea is to map range. And so I'm going to pass the VA. And what do we need to pass? We need to pass the destination virtual address, which will be right here. So here's where we do these prints. And yeah, so we're going to print number 1. Virtual base is our base address, and this is going to be map range. And then we need to keep going, of course. And so next up, physical address. That's going to be phys base. Lastly, we need our length. And I might just hard code this. E1000 is hard coded based off of the length of this region. So that's sort of what I'm thinking for the moment. Right. And I'm just going to run this and just, my expectation is that we're going to hit the panic 1, 2, 3. I'm just mapping memory, but I'm not switching into these page tables yet. And so I fully expect to just map the range and then hit the panic, and then that's it. Once we see that that works, we can take the next step of actually trying to switch into the page tables. And that seems to work. We hit them 1, 2, 3. Okay, so now it's time to switch into the page tables. And formerly we did this with load CR3. And here's the part where I'm gonna probably lean on the AI. Please generate a 64-bit version of this function. I ran into this with read CR3 earlier. And yeah, I'm not really so familiar with inline assembly. I can sort of read this and get the sense that it's moving this thing into CR3, which sort of looks like AT&T syntax to me, but I'll just ask, is this ATT syntax? Actually, I think I cannot ask questions in that inline mode. Yes. Right. Is it possible to write inline as in with Intel syntax? Genuinely, I don't know. Per block directives or big compiler flag on the whole thing. And you get some benefits with Intel syntax, like no need for the percent, no size suffixes, and the order is different. I'm not going to worry about that for the moment. I'm also going to quickly check into JOS. It's been a while since I have done something like this. So here's how you use it in JOS, which, by the way, JOS is this JOS OS that I keep referencing. This is the OS that's from that MIT course that I was talking about, that class that I did, this OS that I got so familiar with over the course of 2024, basically. And so I'm often referencing it because I know it worked and I know sort of how it works. And this is an example. And so load CR3, you pass a physical address into load CR3 and it triggers a page table switch. And so what we would do basically is we need to pass here. Oh, this exactly this thing. Oh, phys PML4 table. Physical address of the PML4 table. Over here, we're passing the physical address of the page directory. On 64-bit, we pass the physical address of the PML4 table. And yes, running code. Oh, code with own maps. So now I expect this to fail because even though we're mapping this range, I have not set the executable bit on my mappings. Going back to the page table layout, we have the XD bit, which is not some kind of laughter bit. That is execute disable. And maybe, I wouldn't even need to check about how this works, but a lot of things are kind of wrong here, I think. So in my page tables, I've been leaving pretty much all of these flags at 0. And actually, you know what? I'm realizing there's a bunch of things I might need to double check on. And so 0 initialize the PTEs. I don't even know if I've been 0 initializing things that I need to. So executable bit, RWX permissions, and propagating flags across the page, the table levels. I don't know that I've done any of that really. So yeah, it's something we need to double check on. Okay. And as usual, we'll go one step at a time, but okay, just to again take baby steps, I just want to observe the crash that I'm expecting. The goal is to see the panic with this text, and we're not going to see that for some time, I think. Right now, we're just expecting to see an infinite boot loop when it crashes. Yep, that's what it looks like. That's what it looks like when your kernel crashes and you have not set up interrupts or anything like that. It just boot loops. And so now let's try to work through some of these issues. Let's start off easy. Let's start off with the 0 initialization. Question. And so we need to dive in here into here. And so I actually want to use memset instead. I think fill n, it's a bit more C++y, but it's actually not as efficient, I think. Okay, I also have realized I need to switch my clang D. No, my compile commands to point to the no. I think it's over here. I always get so commands. I don't want to be finding the macOS memset. I was already using the target ones apparently. That's kind of annoying. Oh wait, it's in the .clangd. Yes, I think for some reason I started using this file. Target. Let's try this out. So what? So if I modify my .clangd, do I reload clangd? Now let's see memset. Yes, that's working now. So now when I go to definition of memset, I'm no longer going to the macOS SDK. I'm going to the memset that's defined within my kernel. So v3, how do you code with AI? It's impressive. I do code with AI, I just don't do it all the time. Yeah, I think I prefer to not code with AI because it makes my brain work harder and I learn better. But there are certainly instances where it makes sense to use AI, and I do that in those cases. Like just now, I just changed that one line, but overall, I'm not trying to generate massive amounts of code with AI. I probably could try to do that. That might be interesting, but that would serve a different goal that I'm currently working towards. Okay, so step one. So here we see that I'm allocating a PML4 table. I do that up here actually. I can actually move this line down, I guess. Allocate the PML4 table. Convert it to its virtual address, and then memset it to 0. Which is good. Now we need to dive into the virtual address space to understand what kind of 0 initialization it's doing. And let's just walk or alloc. And so here's kind of the key function: get or allocate next page table. And the key part here is where we alloc. Thanks, hee. Vibe coders are ruining the job market. Oh man, those vibe coders. Dang. So here's a bug. Yeah, we are not clearing out the memory here. That's bad. So probably that needs to happen here. And maybe let's try using AI. So we need to zero out the new table, convert it to its vert adder, then call memset. Let's see if it can do that. It probably should be able to. That's not so hard. Right, so we grab this thing. We've checked that it's valid, and so we dereference it, get the get the virtual address, and then we can use that. What is the type here? It should already be void star, right? This returns a void star. I don't know why it put a reinterpret cast there. So I'm guessing this is sort of what we need. Maybe even better would be to add an API for allocating 0 initialized memory. That could be nice, but for the moment, this is good enough. Or just have the idea, I mean, we could just make the API always return 0 allocated memory. Is there a use case where we would want to allocate a frame of physical memory and then not 0 initialize it? If we know that we are going to overwrite every byte in that frame before we read it, maybe that's slightly faster. But actually, you know what? I sort of like the idea of just always always zeroing it out. Which creates one problem, because then the bitmap frame allocator needs to know how to do address conversion. And it currently does not, never needs to do that, and so we would actually need to pass in a reference to the allocator, and it's all annoying. So you know what, never mind. I'm gonna go just leave this here. Let's see if this compiles. We get a variety of cast warnings because string is not meant to be used on 64-bit. So that's sort of why that is. What is this even doing? Takes a, okay, uint pointer t. Because int is not, yeah, casting it to an int is not what you want typically. So, okay, so anyway. Similar problems here. And lastly, like that. What? That's so strange. Why does it start to compile error if I make this change? Okay, you know what? That's a problem for another day. Let's stay focused. So here, question number one. Okay, here we are mem setting all the entries to 0, so that's good. Any other places that allocations happen? I don't think so. No, it's a single place we do allocations here. So that's number one. Now let's talk about bits. Currently, the memory mapper is only doing the most minimal set of flags or settings in the entries. It's setting the present bit to 1 and the frame number. This is in every layer of the page table, but then also finally at the very end we do the same thing. And it's completely unaware of flags or anything like this, and so that's kind of a problem. I think that's a problem for another day though. What I'll do in the meantime, as the fastest way to just easily make progress with the most important thing, is I will start setting some very liberal permissions. So I'll start setting the write bit and the execute bit, I think. Double checking. So if 0 writes are not allowed, this is not the right part of the documentation. It's all kind of the same anyway, but page table entry maps 4K page. 0 writes are not allowed. 1. So we want to set this to 1. And so let's go ahead and do that. Writable equals 1 and no execute. Wait, so what? So then how does that bit work? So execute disable, but okay, if, interesting. So I didn't actually know this. If some special register is set, what's up off market? Nice to see you. Thanks for joining the Twitch stream. Okay, so apparently I didn't really have this totally in mind. You need to opt into using no execute. Execute disable, otherwise reserved. Okay, so I have not enabled this yet, and so that means there's no execution permissions actually. So we don't need to worry about that. So all we need to do is go here. And so now we've set, now everything that we're mapping is RWX memory, I believe. We can quickly peek at the struct definition. That's how I'm doing it. So now what I'm thinking about is I'm trying to guess why that boot was failing. My theory was that it was because there was no execute enabled, but we haven't even enabled at all, unless the bootloader enabled that for us, which is very possible, actually. Question. Do I have the Limine source code around? I do. I don't even know. Yeah. Let's just code this. Right, so this is the code of the bootloader that I'm using. And I'm just searching for NXE, and it seems like it enables it. How Limine 32 x86, I don't quite understand that, but okay, Limine 32. I'm using 64-bit. So here's all the protocols, right? Linux boot protocol, multi-boot, blah, blah, blah. I'm using Limine protocol. IA32 would mean 32-bit. As x86 means 64-bit, but this is 32, so. The reason, bits, there are, but wait, but this, IA32, okay. Somehow, something about that is 32-bit, which is surprising to me because in normal 32-bit x86, there isn't a no execute bit in the page tables unless you have physical address extension, I think. And I sort of thought no execute was a 64-bit thing, so it surprised me that there's 32. The whole point of me saying that is it's plausible that the cause for the crash is because Limine enabled the no execute bit for us, basically. Okay. Which would mean that we actually do need to set it here. And so I'm just going to do another baby step forward. I might also just start doing some commits. Add R364. Whip fix compiler warnings. And this is all kind of the present whip code. Whip try basic map in kernel. Okay. So what's the prediction? The prediction is that the kernel is still going to crash. Even though we're setting the write bit, that wasn't really the reason for the crash because there are no memory writes happening right now. It's all about execution. And since Limine started up, enabled no execute, and we still have not set it in the page tables, we're still going to crash. And we're still crashing. Good. What's up, check wob no execute was part of the proper protection system in 32-bit, which was non-executable memory segments. Oh, interesting. TIL. Thanks for the info. Okay. So let's finish it off then. Let's do what we need to do. So apparently this is on. So if this is 1 execute disable, which means if one wait, okay. If one instruction fetches are not allowed. So that sort of blows my theory apart, because we're currently setting it to 0. And so that sort of means they should be allowed. This is sort of like, is this writable? Is this present? Is execute disabled? So actually now here's the part where I don't really know why. Yeah, here's the part where I don't really know why the load CR3 now starts to immediately crash. Just for fun, let's try debugging it. Can we debug? I am forgetting. Oh, I think I need to go in. This is sort of annoying. I need to go into here. Okay, so now here's the part. Break K main. Oh, interesting. Why does my LLDB looks kind of different than it used to? Almost there. I could have set a breakpoint in another place, but whatever. Call. Why is it's interesting that there's a call there. Let's just step through. Oops. So watch out right here. Here's where we're going to step into it. And we're going to step into load CR3. This is pretty much all there is to it. Move CR3, blah, blah, blah. So the expectation is that we're going to hit this instruction, and then the next instruction is going to reset the machine. Yo, so off market, you're asking how to learn to program like at all from scratch. That's a super general question, man. And yeah, it's also not like, it's something that there's a lot of ways to try it out. Like, have you tried a tutorial? Have you tried looking up some projects to try to do some just basic projects, like try some Python programming? Yeah, I mean, that's a good start. Yeah. All right, let's step over here. So watch out for over here. And we're approaching the CR3. Okay. I'm gonna run this instruction. That's gonna succeed. The next instruction is gonna fail. That's my expectation. So I'm gonna hit enter. Bam, we did it. This very next instruction, pop RBP, that's the one that's gonna fail. That's my expectation. Step instruction and the machine reset. So far I haven't learned anything new. other than I've been forgetting to take the break, so let's go ahead and take a 20-second. I just don't want to be stuck in a tutorial loop then give up. Yeah, I mean, you don't need to don't do tutorials forever. Just do enough tutorials until you have learned a basic concept, and then stop doing tutorials and then just try using what you've learned, and then ideally find some kind of project to work on though. I think that's my advice. Like an app or something, or a command line tool that cleans up your, I don't know, folders or whatever it is. And then just find something like exciting and useful to you and try building it. That would be my advice. Okay. So far I haven't learned anything. I simply have this mysterious kernel crash. I'm gonna take some notes. So it's enabled by Lemine Weeb, I believe, but our XD entries are 0, meaning execution is allowed. Write set to 1, although we don't need it yet. Done. Flags propagating across page table levels. That might be kind of interesting. Okay, one alternate idea actually is I could initialize my vAddressSpace class to actually take ownership of the existing PML4 table that Lemine created. If my only goal is to test whether a basic mapping works, I can do that within the context of this existing working virtual memory address space, which Lemony gave us, and just try to do that. So that is also another idea. More direct test, take map page within existing Lemony vAddr space, then try to access it. And that might avoid some of these random questions about kind of changing the entire address space. So currently boot loops, and unsure why. Really the main theory is that the page tables are configured wrong, would be the guess. What's up, Kushagra? Have you ever tried binary exploitation pwning? I've done a little bit of that. Yeah, I used to do some CTFs years ago, and I used to work in the security industry. But it's been a long time since I've written an exploit. However, a lot of these skills that I learned about how to step in a debugger come from that world. So yeah. So what's up, my Yusuf? Hey there. Off market. Which one do you prefer learning, from a book or watching YouTube videos? I think probably YouTube overall, I would have to say. I've read some books, but yeah, probably overall watching videos. That's the current guess. And so what could we do to debug this? We could examine the PTEs more in depth. There's also this this info mem command. I want to learn more about this. And here's where I might hit up the old internet. Info mem. So what's the deal? Show the active virtual memory mappings. Show. So this sounds very useful. The QEMU monitor has all these commands you can run, apparently. And how do I use the QEMU monitor? Okay, let's try this thing out. Monitor dev, monitors, did I have it? Okay. So let's go to the dev tools, that's CMake. Let's look at our QEMU command. Kind of new here, it came from the OS playlist. Seems much appreciated, internet needs such content. Thanks a lot, I appreciate it. Glad you are finding some value in it. I feel like I'm just sort of like not knowing what I'm doing a lot of the time. But if that's helpful for you, then I'll take it. Okay, monitor dev, right, monitor.io is the example here. So I wonder, what can I do with this? Can I, like, what even happens if I run this? Oh, can I use std? I have multiple character devices. Interesting. I'm already using std.io for the serial port. So what if I just don't do that, but then do this instead? Can I debug it still? I can debug it. I can run. Cool. So now, oh, well, also what? I'm still getting output even though, okay, did not expect that. But anyway, let's try this out a little bit. So QEMU has all these commands, apparently. Let's just info registers. Can I do this? Whoa. So we can print out some information. You can dump memory, blah, blah, blah. You can read IO ports, and that's all it says. So all right, let's try it. Info. I wonder what this means. Oh, this is the information about the what's currently in the TLB versus the memory tree. I wonder what that is. Okay, let's start out easy. Info mem. So it sort of does. That's cool. Why is that so small? It does a page table walk. And prints out some ranges. And why is the screenshot so low resolution? Is this just huge or something? I don't know. Okay, it prints out the ranges. This is kind of neat. So what we can see here is broadly, we have the HHDM here at this F8 half region, and then we have the kernel, the kernel's mapping here. And it's interesting that there are 3 distinct segments, it seems. Coding bananas. I sort of understand it. I mean, yeah, no, actually, I completely understand it. It might seem overwhelming, but this is just expressing what are the ranges of memory that are currently mapped. This is the length, this is the start, this is the end, and these are the permissions. So that's interesting to see. Something that is immediately standing out to me. Oh, did I mistype? Okay. E1000. So this is the amount that I passed in, because I sort of just assumed that was the whole length of the executable and modules, and if I was able to map that into the address space, that would be sufficient. But it's sort of looking like that number is way too small. Or actually, how are you even supposed to interpret this? Oh, wait a sec. No, did I mix it up? This is the HHDM, maybe. And then this is where the kernel's mapped. I think it's easy to get confused. I got kind of confused with that. Yes, this is the halfway. The confusing thing is that this is halfway through the address space, but this number has half F's and half like not, and so that sort of made me think that that was the halfway number, but it's not. Okay. What's up, Anatoly? Peace to the world. Yeah, you'll get there, Coding Banana. I mean, if you're on a Linux system, you can just kind of get a look at it. If you're, I'm not on a Linux system right now, but if you have a Linux system, just do cat proc self map or proc self maps, and that will print out for a Linux process what the memory maps are for that Linux process. It'll be very similar to this, and you'll get some experience reading these kinds of maps. And I totally going off in the chat. Peace to all. Yeah, for sure. Okay, so I take that back. This is where the kernel is mapped. This is where the HHDM is. And then that explains these numbers a little bit more. And we're seeing the 3 segments of the kernel being loaded at various places in memory. And what I was doing is much more coarse than this. I was just doing a blanket, broad memory map. And maybe that's the problem. So maybe I need to actually elf load myself, which would be kind of annoying, I have to say. So there's a few directions we can go. So I'm gonna elf load myself, or I can just copy these mappings. Also, try using info mem on whatever state I generated. That's what I want to do first. I want to try just doing info mem, but after I engaged my page tables, and see what even happens. Does it even have anything? Because that would even indicate how broken my page tables are. So I'm going to try again. BK main. Let's do CR. Yeah. So now we're going to continue. So now we're all the way here. And pay attention to right here. Right. We're right there basically. So if we do info mem, this is what we're expecting to see. I'll do a step instruction to move past that. Engage my page tables, quote unquote, and let's run this one more time and see what happens. Oh, check that out. So I think that's great. That's great news, actually. The fact, so I ran this after engaging my page tables, and we're seeing that it could actually, QEMU's implementation of page table parsing could actually see the mapping that I wanted to create. And it looks completely correct to me. E1000, and that's completely consistent with the fact that I hard-coded hex E1000 in my code. So that's a small win, I would say. So small win is that the page tables that I'm generating are not completely structurally broken. The problem, so this seems to be working, and so the problem now is that there's some problem with the actual mapping of the code of the kernel. The code of the kernel was previously I don't know, maybe this first one or something like that. And after I engage the new mappings, for some reason, the code of my kernel is not appearing at the exact place that it used to. So 22nd. Actually, interesting. Check WAP is your stack. Actually, that is a good question. That is a very interesting question, because the next instruction is pop RBP actually. So that's actually, yeah, check WAP, you get points today. That's a sharp opposite. I hadn't thought of that. I was assuming that the problem is with instruction fetch, that even fetching this instruction was was faulting, but you're saying that it's not the fetch that's the problem, it's the pop is the problem. Reading the stack pointer. You might be completely right about that, actually. Yeah, that's good thinking. Myosef, can I share your GitHub handle to refer portions from the playlist? So this project that we're working on is not on GitHub, unfortunately. You can find my GitHub is there. It's offline mark, but the kernel is not there. I just want to keep it private for now. That is super sharp. Let's think about that. The stack. Yeah, our stack is not mapped. How? And I'm thinking actually, yeah, that's probably it. Well, maybe. I mean, it's also probably that. It's also possible that, I don't know, the elf loading or whatever. I sort of just assumed that the kernel could just be like mapped into memory. It is very possible that that's not the case. So let's say I wanted to map the stack. Yeah, you're saying info registers, right? That would reveal RSP. And so so that's the current RSP. So at a minimum, that needs to be mapped. I guess that's what you're saying. I guess what I wanted to know is like how much of the stack do I need to map actually? Where does the stack start and where do I even get that? I mean, so as a quick hack, yes. As a quick hack, yeah, let's try it. So, so we're going to copy, we're just going to, but yeah, but the question is, where do we map that to? And we can always use the fizz map adder converter, I suppose. So, okay. void RSP. This is so sketchy. Okay. Right. So that was like our kind of working RSP. So what I want to do I'm just going to align that, right? I'm going to align that, and then I'm going to use the converter to convert this to phys adder. I'm going to convert that to its physical address. But here's that thing again where it thinks it needs to cast and it like doesn't. Okay. And I don't know if I'm going crazy, but okay, let's say, yeah, so we like hackily grabbed the RSP at the point we're converting it to its physical address, to its physmap address. Which I have some questions about, but like one quick rewind, let's just look at this memory map real quick. Where would the stack be? It's going to be somewhere in here. It's going to be in one of these bootloader reclaimable regions. Wait a sec. No, I think this conversion is going to fail. This address, or is it? This address looks like a physmap address to me. So that means it actually might succeed. Which means the kernel is running out of the physmap on this stack. That's interesting. Maybe just a quick, I know I'm saying a lot of like words right now. I'm just trying to, if I dry it out real quick. So we have physical memory, and then we have virtual memory, right? And then we have, okay, so no, physical memory, this is this full 64-bit space. Physical memory is super limited. It's like, this is not to scale, but it's like a very low amount of physical memory. And then over in the virtual area, we have two regions. We have the high region, and then approximately halfway, we have this, the physmap. Let's make this a bit smaller. Oh, let's make it more precise. So this thing exactly maps to this, right? This region exactly points here. And then this whole thing, right? And there's like gaps in here, and then a certain chunk of this thing wherever I'm gonna make this even smaller to sort of emphasize that it's like not big. Some chunk of this thing points here. That's sort of the situation we're looking at, and the question is like RSP blah blah blah. So this is a physmap address, which means it's pointing. So RSP is pointing. like somewhere in here actually, which corresponds to somewhere in here. Zooming out one level, the question I'm trying to answer is, okay, I have a virtual address for the stack. I need in my code, I need to have some kind of physical address to map it to. So I'm trying to figure out what is the corresponding physical address of the stack if I only have a known virtual address. And because it's within the FizzMap region, that's easy to answer. I just need to compute the offset from the base here and then apply it over here. And that's what my FizzMap adder converter does. The problem would have been if it is outside of this, outside the FizzMap, I can't just use the FizzMap adder converter with the simple addition. I think I would actually need to walk the page tables to figure that out. But luckily, it seems to be within the FizzMap, because when we enter from Limine, we don't have that many mappings. It's just the kernel and the FizzMap. And so I guess it's sort of natural that the kernel is running directly out of the FizzMap for the stack, which, and the reason I find that important to point out is that's not normally how things work, if I understand it correctly. Normally, you explicitly map a region for your stack, and because there's gonna, like, different kernel threads will even have different stacks, and so you are explicitly mapping stacks. You are not directly running out of the FizzMap, because from what I understand, it's also kind of dangerous to run out of the FizzMap, because what if you overflow past the end of the stack? You don't necessarily know what is in physical memory right below the stack. You might corrupt some stuff, I don't know. So that's just to explain why I was a little bit surprised to see the stack pointer in the FizzMap, but that does make sense for where we're currently looking. So yeah, what's up, Straticus? Nice to see you, dude. Finally installed a Linux distro. Sick. Which one did you choose? I gotta say, I'm not really a big Linux like distro like wizard or whatever. I have pretty much only ever used Ubuntu in my life. All right, so let's do this. So we got our hackily harvested RSP. I aligned it just for reasons. We're converting it to a physical address, and then now what we need to do is map a range. And really, we could do this in a single call. We're going to sort of hard code this, I guess. We're going to RSP aligned, and we're going to map it to PH RSP aligned. And we're going to map page size. We're going to map one. And what is the problem? Oh, okay. This needs to be a vert adder. Okay, this is a little bit of annoying casting I need to do or whatever. I need to convert it to a Unit64T. Apparently. Whew, okay, whatever. So check WAP. Yeah, without RPages, that's concerning. Yeah, it's sort of, I don't know, it sounds a little bit sketchy. So anyway, thanks to CheckWob's insight, we're now trying to make, like, this is kind of crazy that we're like hard coding these addresses, but just to sort of try to even see this a little, like, work a little bit, we're manually going to map in this chunk of the stack into our virtual address space. And it could be possible that is all that is needed to keep going. So let's try it out. So we're going to make the kernel. We're going to again go to debug. I'm going to restart the debug session. We're going to break on read CR 364. We're going to continue. All right, let's check it out. Disassemble. We're pretty close. Now this is interesting. I feel like the code changed a little bit. Am I wrong about that? Did I not copy paste the code? Okay, I sort of thought I did. Anyway, I could have sworn there was more like stack stuff up top, but whatever. Okay, so we're going to do info mem just to, okay, we're still on the liminy bootloader page tables. Step instruction, bam, engaging the new page tables. No? Wait, what? Whoa. Okay. What? Oh shit! I broke on the wrong symbol. It's loads. Okay, back here. So this is more what I'm looking at. So that's what I thought. So we're stepping. Info mem. Okay, we're still on the liminy. One more step. We're going to engage our page tables. Right. Bam, and check it out. We have our new page tables mapped. They have two entries. One is the high mem, the kernel mapped in, hopefully into the exact same place it used to be. And then thanks to CheckWob, yeah, we got one page of stack mapped. It does not show physical addresses here, but moment of truth. Does the pop RBP run? SI, let's check it out. Ready? Holy shit, it ran. Yo, CheckWob. You were right. CheckWob gets the gold star for today's stream. Seriously, that was a sharp insight. So, yo, we're running. The kernel has been like surgically migrated off of like, you know, the initial page tables that you get from the bootloader, and for the first time is like running on its own page tables, which is pretty cool. Heck yeah, for sure. I'm gonna call that a win. That's a big win. And I think what I want to also just say is the problem was because of the stack. It was not because this mapping is wrong, actually. And so actually it's sort of it's cool that all of that page table construction code basically worked on the first try. And of course it's not really the first try, but it's the first try in the actual kernel. We spent all this time working on these unit tests that like go to like quite incredible lengths to try to validate the structure of the generated page tables, but that was all in the unit test. And so there's always a chance for things to go wrong in the meantime, but it actually seemed like that sort of worked. Like really the structure of the page tables was totally correct. QEMU was able to read them and we're able to use them. And so I wonder even, are we going to just hit the panic? Are we going to see that panic? As a reminder, panic, yes, running kernel code with own maps. I'm going to hit continue and bam, we see it. Panic, yes, running kernel code with own maps. Whew. So now that is exciting. That is cool. I mean, yeah, for maybe a very experienced OS developer or whatever, like that's like, it's like kind of normal to switch page tables. But for me, that's actually quite exciting. I haven't, I worked on all that JOS stuff before with the MIT course, but it didn't quite have the same feeling to do it like myself like this. So that's really cool. Yeah, there's a lot of open questions, I think, still. I mean, the stack situation is very interesting. This was enough to get the next couple instructions running, basically, but it's possible that I'm actually missing like stack pages that are higher in memory, just because I don't really know how large the stack is. I wonder if we can just pop open into the Leland protocol and read a little bit about this. RSP is set to point to a stack. Right, so I'm looking at the documentation, which describes all about like the initial entry state, and RSP points to a stack in bootloader reclaimable memory at least 64K. I'm gonna kill the palm tree. But the question is, can you query the top of the stack? What I want to know is, like, where did the stack start at? And I don't even know if there's a request for that. There is the stack size. So I can request a stack of a certain size, but I'm trying to query the starting point of I actually don't see that. So yeah, I don't know how useful of a feature that really is, but for the current moment of my goal to like map the stack into my address space, that would be kind of handy to know. All right, so that was cool. Very exciting. Again, taking the screenshot for some capturing the memories purposes. Check Wob gets the star for today for pointing out that the stack wasn't mapped. Yeah, I think that's going to be the win for today. We're going to kind of wrap it up here. Let me check in on the chat. So first off, Scraticus tried Pop OS first, which then had clashes. Now in Cashy OS. Dang, Arch distro, pretty far. Having fun. That's good, man. Never tried Pop OS, never tried Cashy OS before. I heard it's very popular these days. I was always just kind of a Ubuntu person and never really broke out of that. Why use LazyGit when VSCO has Git inside? Kevin McAllister. I use LazyGit because LazyGit is the most powerful Git client I have ever seen, and it's really fast to do a lot of Git operations like splitting commits, reordering commits, stuff like that. What language? I'm using C++. Are you using any AI? Yes, using it sparingly, but when it's the right moment. Where are you getting these MD files from? Those MD files, these are in this thing called Limini protocol. Limini is the bootloader that I'm using, and it has documentation. And so if you just search for Limini, and you can find this documentation on the internet. Why don't you use Rust? Good question. I would love to use Rust. The whole problem, I just don't know Rust, and I'm trying to make this easy on myself and introduce as few new hard concepts as possible. And so learning OS development is hard enough as it is. I'm very experienced in C++, and so I'd rather use something I just know more, I'm more comfortable with. Seeking one suggestion for today, best way to deep dive with kernel space versus user space after your blog. I would say start with user space and just learn about memory mappings and stuff like this. Like learn about page faulting, read a bit about Linux kernel code. That's how I started. For years, I was just like reading Linux kernel code, like reading about how the page fault handler works, doing experiments. I'll just show you my blog. Like literally years before I started doing OS development, I was learning about Linux via blogging, and this is from 2021. I was writing these blog posts exploring about how memory permissions work. I was exploring about how demand paging works, and I literally hadn't written a line of kernel code. I was just like writing user space code that would do mmaps and sort of like play around with how that works, and I would read the Linux kernel, and that's what I was doing. So where did my thing go? Are you doing this purely in C++ or is C and assembly included here as well? Yes, there are some of both. Some of my string routines I like ripped out of JOS, and they're written in C. And assembly, actually, because I'm using Limony, I don't have assembly at the moment. Like really, I mean, I'm not really counting these like small little like inline functions for like doing specific instructions, but probably more in the future when I do context switching and stuff like that, there will be a bit more assembly. Is C the best programming language for use for self-study or Python? Second year CS. I mean, they're both good languages to know. For the longest time, those were the only two languages that I knew until I learned C++. I would say they serve very different use cases. They teach you about very different things. And ideally, you would have experience in both of them, I think. Yes, Home Alone. Are using Vim motions in VS Code? What are Vim motions again? I don't actually really know what Vim motions are. I try to use, I mean a little bit like VIA or whatever, or like, you know, DAP, delete paragraph or whatever. So I try to use a bit of that. What specifics in kernel code? So, oh, actually, yeah, I use them. I use like E and stuff like that. Oh, yeah, I'm using that kind of stuff. Yeah, when I move around in Vim. Yeah. What specifics in kernel code? Okay, what I would just say is, learn how memory permissions work. Like, write some code that calls mmap, and it maps some executable code, or maybe read only code and read write code, and then do some memory accesses into these regions and understand how that happens. And that's going to require you to understand what a page fault is, or like how page tables work, which is what we've been doing today, basically, but you'll be in a bit more of a comfortable environment in Linux, and just read some kernel code, maybe ask the AI. Yeah. All right, y'all, it's 6 p.m. where I live. I'm gonna have to end it here today, but I wanna thank you very much for joining me for the stream. Thanks again for CheckWab for that insight. We reached a nice checkpoint. The kernel is running in its own virtual address space for the very first time ever, which is a small win, but I'll take it. A lot more work to do, but that was exciting to see. So, yeah, okay. I'm going to ask some favors of you. Please subscribe to my YouTube channel if you're watching this right now. I don't even know how many people are watching. 20 people are watching. If you are literally watching right now, if you're enjoying what I'm doing, I would really appreciate it if you subscribed to my YouTube channel. And join the Discord if you want. There's a Discord server. Let me get the link for you. Or maybe I have a Discord bot. Discord. So I would just say, walk a simple example, just like, just try going to my blog and just like read a few of my blog posts about the Linux kernel stuff I was showing. And even that would just be a good starting point. Just make sure you can understand those blog posts, and even that will get you pretty far. And we can talk more about it in my Discord. It's just super fun for me. 6 p.m. sheesh. All right, y'all, that's going to be it for today. Thank you very much. Have an amazing week. I will see you next week. Peace.